So what we have done so far, let me just recap a little bit so that you know where we are going. In this chapter, we have gone through Newton's laws, 1, 2, and 3. And so you are actually capable, or you should be able to answer all sorts of questions from Newton's laws. How do you tackle these problems? Now, there are numerous problems in physics related to Newton's laws. You can't be just going through all of them. You have to think fresh for each question. It may involve a pulley. It may be involving friction. It may be a connected objects thing, or different varieties. How do you tackle those? It's purely an aspect of application. So you apply the laws. Now you did go through first law, second law, and then third law. Now we can see that, like most places we are applying the first law and the second law. Third law is just there to indicate that forces come in pairs. But otherwise, the laws first and second are pretty important when you think everywhere. Now, when forces act on an object, you can have the object in equilibrium. What is the meaning of equilibrium? Net force is zero. And those are the kind of problems that we did, right? So you can have a net force acting on an object, keeping an object in equilibrium, which means it's at rest or moving at a constant velocity. In other words, there's no acceleration. So that's when we apply the first law, right? Now, if the forces are not balanced, then it is definitely going to accelerate. And how we find out that acceleration is by taking the second law. Net force equal to ma. So these are the two types of questions that you can actually, or situations you can come up with. You can have a static equilibrium situation, or you can have something in motion. All right. So we went through different examples. We went through an elevator. We went through a person inside the elevator. So you can see in all cases, what do you do first? Now, first is to draw the diagram. Without diagram, you're not going anywhere. First is a very important thing is the diagram. You draw the diagram, and then next, draw all the forces. If you can get the numbers, put the numbers down. Okay. Draw all the forces that are actually acting on the object. Once you draw all the forces acting on the object, then you apply either the first law or the second law, depending upon whether it is an object in equilibrium or if it is an object which is expected to accelerate, right? So we applied that way, and we went through so many different examples. But today I'm just going to introduce you to friction, and once you get introduced to friction, then you should be able to incorporate friction into the similar problems. So we will actually go back to those problems and do it. So let's do a variety of problems now, including friction. So what is friction? What is friction? What is friction? Friction is a force that opposes motion. So friction is a force that opposes motion. Now there are two kinds of friction. One is called fluid friction, and the other one is called solid friction. Yeah, fluid friction and solid friction. What is a solid friction? Solid friction is the friction between two solid surfaces, like this book and the table. All right? Solid friction is the friction between two solid surfaces, between the book and the table. Or the rubber tires and the road. Those are solid friction. Friction between two solid surfaces. And you already know microscopically what exactly is happening, right? So between the surfaces, there are lots of molecules kind of standing up like grass, and it just sits on it like this and grips. So when you try to drag it like this, you're disturbing the shape and formation of those atoms and molecules, and so they will try to pull back on you, and that is basically what we experience outside as friction. So friction, solid friction is between two solid surfaces. What is a fluid? What's a fluid?
Isn't it a gas or liquid?
It's a gas or liquid. Anything that can flow is a fluid. Anything that can flow is a fluid. Gas. So air is a fluid. So we are at the bottom of a huge ocean of air. So think of us as creatures at the very bottom of the big ocean of air. So air is a fluid, and we are at the very bottom of that. Now some fish, they go to the bottom of the ocean, so that's a different one. So water is a different fluid. Above that is air. We are actually moving in that fluid. Okay, so, but the air is slightly different from water, because as we go to higher altitudes, you have density of air going down, right? So the atoms get spread out a lot more, so density becomes smaller and smaller as you go higher and higher. And if you go 50 miles or 100 miles, finished. There's no more air. So the blanket of air is over. 50 to 100 miles, that's the maximum. So if you go above that, it is purely vacuum. There's nothing. Okay? So 50 to 100 miles is the thickness of. So if you go to around, 10 miles height, there's hardly much air. Very, very little. There's very little air. So obviously the oxygen level is also going to be low. So if you're going to do cross country, for example, it's a nice thing to practice cross country running on a mountaintop. Because if you practice over there, you are having less oxygen to deal with. And so if you are able to run well in that situation, you should be able to run much better here, because you'll get a lot of supply of oxygen here. Yeah, so that's why we feel tired when you're running at high altitudes. You can actually easily get tired because you don't get the required oxygen to do the burning. So what is solid friction? Solid friction is friction between two solid layers. Friction between two solid layers. That is solid friction. Like a layer of the book and the layer of the surface. So you have solid friction. Okay? Fluid friction is friction between two fluid layers. Normally it is of the same fluid. The layers will be of the same fluid. That's called fluid friction. Now, you won't be able to see the fluid layers that easily with your normal eyes, because you don't see the arrangement of atoms and molecules, so therefore you don't see the layers. But you can understand the presence of layers. Say, I'm standing here. Is there a layer of air bonded with me? Can you imagine that? Is there a layer of air stuck to me? Yes? Because it's adhering to me. And now there is a layer of air just outside that, which does not belong to me. It belongs to the room. So when I start moving, what is happening is I am moving with the layer that is stuck with me. But the other layer is outside. So they start rubbing against each other, and that rub against each other causes a drag, and that is called friction, fluid friction. So the drag that you experience is between the two layers. Now layers you don't see, but that is the fluid friction. So you don't see those layers, but it is already there. It's like same thing as a car. Your car, there is a layer of air stuck to the car, but when you drive, that layer is going on the road, whereas the other layers are on the road, so there is a rubbing effect on that. And so there is a drag. Which one is dragging what? The stationary layers are dragging the moving layers. That's how fluid friction works. Yeah.
So is there an instance where like there can be friction between a solid layer and a
No.
fluid layer?
No. So when you talk about solids moving in a fluid, we are talking about the fluid layer that is stuck with the solid and the outside fluid layers. Okay? It's like this. Imagine there is a 3-lane road. Imagine there's a 3-lane road and people have parked their cars on one lane. Can you confidently drive on the next lane? No. You'll be always like, will somebody open the door from that, you know? So those stationary lane of cars slows you down or drags you. Okay? Those stationary layers are going to basically drag you. And that is basically how it works. So if there is one layer moving against the other layer, the stationary layer drags the moving layer. And that is fluid friction. Now fluid friction depends on what factors? Let's investigate that. Yes, fluid friction depends on
Temperature or density of the fluid.
temperature, density, and everything is put together in one word, nature of fluid. You can also use the term viscosity. You know, nature of the fluid. Yes, depends on the nature of the fluid. Not all fluids are exactly the same. Some fluids are more frictional than the other, right? Let's say, for example, imagine you have a tall jar of water and you have another tall jar of honey, and you take a steel ball and drop it into this tall jar of water. Can you visualize what will happen? Yeah, I know you've not done this before, but you can easily understand what should happen. As soon as you put in the steel ball into the tall jar of water, you can see the steel ball going down, not like that, but definitely slower, right? It goes down to the bottom. Now, if it's the same steel ball is dropped into honey, you can imagine that it'll be pretty slow because the drag on it is much more. So nature of surfaces, nature of fluid. Nature of the fluid is one of them. Then, what are the factors? What other factors do you think is important when you talk about fluid friction? Anyone? Doesn't matter if it's right or wrong. Just go ahead. If you have a faintest idea, go ahead. Yes?
What do they container it in?
The container, you mean like a wider container, a narrower container?
Yeah, or like the type of container, maybe.
If it is a wider container, yes, there is a difference, because in a narrower container you have stationary layers right on the other side, and you know, so there can be more drag. But let's say, for example, a car moving on a road, like friction. What does it depend on? Yeah.
Like if the car, the shape of the car, like if it's like a
The shape of the car
like if it's a truck.
matters. Yes, shape of the car matters. That's why they kind of make it more aerodynamic. You know. Let's say, for example, there are two people in knee-deep water. Can you imagine two people in knee-deep water?
Yes.
Yes? Two people knee-deep water. One of them has fat legs, like that. And one of them has blade-like legs like this. Okay? Now, if both of them are walking through the water, who will experience more frictional force? The fat one. This is going to cut through the water. Whereas the fat one is definitely going to suffer because he has more surface area. So it depends on surface area. It depends on surface area. So that's why you make the car more aerodynamic, so you can minimize the surface area and make the airflow more smooth over it. All right, so if you think of a truck, you know, the truck and the engine that carries the truck. See, if you look at all this area, that's a lot of area. So they put that thing on top to minimize the fluid friction. So just by installing that, they're going to save a lot of gas in the long run. So yeah, making the shape of the moving object more aerodynamic, like the bicycle helmets. you know, they're different because you need to, the air should not be blocked, so you need more to reduce the area. Yeah, so it depends on surface area. That's one of them. What else? Yeah,
Mass.
mass of what? Of the object.
Yeah, I suppose.
Mass of the object does not really come in because what matters, I mean, you're talking about the friction, whether it is a heavier object or lighter object. The mass will come in as, you know, with the concept of inertia. So if it has got more inertia, the friction won't matter much, you know, but it is still there. So we're looking at only the frictional part of it, yes.
How fast the object is moving?
How fast it is moving, that's important. Imagine you are standing in knee-deep water, okay, and you're moving slowly in knee-deep water. Compare that with you standing in knee-deep water and just running fast. When will you experience more frictional force? When you're running, it can even tip you forward. Because when you're running, the frictional force is so much on your legs that it'll pull your legs forward and you pull your body forward. Pull your legs backward and pull your body forward. So you can actually suffer a lot of resistance. So it depends on relative velocity. Why I'm saying relative velocity is because if the water current is going one way, you can walk in the same direction without much friction at all, right? And you can be sometimes standing in the water like that and not moving at all, but you'll be experiencing friction. When?
When there's a current.
When there's a current against you, when there's a current like flowing that way, you just stand and it's going to drag you. So that is friction also. So that's why I use the word relative velocity. So friction depends on the nature of the fluid, it depends on the surface area, and it depends on the relative velocity. Now coming to solid friction. Solid friction depends on what factors? Solid friction depends on what factors? Watch this book. When I push the book like that, compare that with that, compare that with that. Any points? Yeah.
Surface area.
Surface area. Does not depend on surface area. It does not depend on surface. It's the same friction. It does not depend. So make sure that you understand that part. Very common misconception is, you know, you get less friction if you just, like if you have a TV box. If you take the TV box and slide it like that, compared to like that, or like that, it's the same effect. Friction is the same thing. It does not matter how it's sitting. Yeah. So that's why I'm highlighting that. It does not depend on surface area. It's a very common misconception that surface area increases, friction increases now. Solid, yes.
How smooth or rough?
Yes, depends on the nature. Nature of surfaces. Depends on the nature of surfaces. Yes.
Depends how much the weight or mass.
It does not depend on the weight or mass. Yes.
Depends on the speed.
Depends on the speed. It does not depend on relative speed. Okay? It does not depend, again. So how fast you move it, slow or fast, doesn't matter. So it does not depend on relative. So these two are very common misconceptions. Yes.
Would it be whether it's already moving or not? Because I'm friction's different ones.
Yes, but that we'll discuss afterwards. Yeah. If it is already moving, the speed does not matter. That's what we're talking. Anything else? Factors. There's only one more factor. What factor is that? Now watch this book as I move it. See this? The book? Compare that with when is the friction more? When is the friction more? The second time? Second time the friction is more. Why? What is the factor?
Force?
The amount of force.
It is not the weight. It's not the mass. Net force.
No, the amount of force.
What changed when I did this?
You applied enough force.
Reaction was greater.
Normal reaction. So basically it depends only on the normal reaction and of course the nature of surfaces. It depends only on two things. Depends on the nature of surfaces and the normal reaction. Doesn't depend on anything else. So when I pushed it like this, what exactly happened is I increase the normal reaction and the normal reaction causes more friction. So friction is proportional to the normal reaction. Frictional force is directly proportional to the normal reaction. Now, look at it again. Look at this book again. How much friction is acting on the book right now? How much friction is acting on the book right now? Zero? The weight of the book? What is it? How much frictional force is acting on the book right now? What is the definition of friction? Opposes motion. It opposes the motion. Is it moving? It's not moving. Is it attempting to move? No. Then why should friction come in? So friction is zero. This book is not wanting to go anywhere. So why should you oppose it? Do you get it? The book is not interested in going anywhere, so therefore no question of opposition there. Opposition comes only when there is an attempt to move it out of this place. Alright, now I'm applying a force of, watch, I'm applying a force of 1 Newton. And I see that the book is not moving. So is there friction now? How much? Is it 1 Newton? Or more than 1 Newton or less than 1 Newton? Now if you say more than 1 Newton, watch. I am pushing with 1 Newton and there is another force of more than 1 Newton, so the book should go that way. Does it make sense? I mean, I'm pushing this way with 1 Newton and you're saying there's a friction force of more than 1 Newton that way, so the net force is that way. So when I push the book like this, the book goes that way. That is practically, wrong. Okay? So therefore, that is wrong. That first part is wrong. I mean, it's not more. Can it be less? If it is less, what will happen? The net force is this way, so what should happen to the object if the net force is not balanced? It should accelerate, but you can see the book is not moving. So when the book is not moving, which law is coming in? First law, which says the net force is 0. That means I apply 1 Newton, the frictional force is exactly building up to 1 Newton and opposing me. Now I increase the force to 2 Newtons. Still the book is not going. How much is friction? 2 Newtons. So the friction is growing as per needs. Friction won't come in unless it's required. It's like this, I'm standing like this and a kid is trying to pull me. When a kid is trying to pull me, I just pull back a little bit, just to balance myself, right? I don't want to pull with 1,000 Newtons. I'm just pulling with just the required force. If the kid is applying something, I apply the same thing. Now the kid is trying to pull more, then I just apply more, just to stay there. So I don't want to pull with more force than what is what is being applied on me. Now, where there can be limits. Now, the kids are joining hands. There are more and more kids coming in and pulling me. And so what will happen is now I'm trying my best to stay. I'm trying my best to stay, but I've got my limits. So there comes a time when I give up. So same thing happens here. Watch the book, I'm applying the force, increasing it 2, 3, 4, 5, 6. The book is not moving. Between me and the book, I have no limits. I can apply a big amount of forces. But the friction has its limit. Let's say the limit was 10 newtons. So I'm pushing 9 newtons, not moving. 10 newtons, not moving, but ready to go. And the moment I increase more than 10 newton, just a fractionally more than 10 newtons, I am successful after that, right? I move the book. So you understand? Friction comes in only to oppose you. Now we are interested in the maximum value of friction that it can hold on to. We call that friction limiting value of friction, maximum. Okay. So the limiting value of friction, the maximum value of friction is this one. Depends on what factors. So the maximum friction that comes in is proportional to normal reaction. And take this off. So the friction, maximum friction is proportional to the normal reaction, and friction is equal to a constant of proportionality times the normal reaction. And this constant of proportionality is called coefficient of friction. It's a constant. It has no units. And this one here is the normal reaction. And that is the limiting value of friction. So coefficient of friction is a constant. Now mu, you have seen mu before. What is mu? Micro. You used it as micro in units and prefixes. But now when it comes in an equation, especially in mechanics, you call it coefficient of friction. So in mechanics, anywhere in an equation, if you see mu, that is coefficient of friction. In mechanics, if the mu comes in as part of a unit, then it is a prefix, micro, right? In some of the chapters, the same mu will be used. In optics, mu is used for refractive index. In magnetism, mu is used for a term called permeability. In different other chapters, we use symbols, the same symbols. But depending on the chapters, you understand what it means. So when you're talking about mechanics, then mu is coefficient of friction. So mu is a coefficient of friction. The friction can be different. We're talking about solid friction. So this solid friction coefficient depends on the nature of the surfaces. Are we talking about book on the table? Or are we talking about rubber on, rubber? Or you're talking about rubber on, rubber tires on the road? Are you talking about wet roads or dry roads? Everything matters. So the coefficient of friction, normally it comes in decimals, like 0.5, 0.3, 0.2, 0.01 for snow, 0.01. And this is the coefficient of friction that really comes in different for different surfaces. Rubber, with rubber, has got a very good grip. Like this number can be 1. What is the meaning of 1? 1 means like even if you apply the weight of the object sideways, it still will hold on. Okay? I can show you something. Can you get up? I want your calculator. Can you see those rubber bushes on the bottom of the calculator? Now these are there for a purpose. The purpose of this is to give extra grip, so when you keep it there and when you start typing, you don't want it to kind of wander everywhere. So this rubber on this table has a good grip. See, when I keep this here, you can see me tilt. You can see it. The table might, the chair might slip. All right, here we go. Look at that. Literally 90 degrees. Literally 90 degrees, and it's still holding on. Okay. So rubber has got a very good coefficient of friction. All right. Now, microscopically, how is friction again? The links are like that. Now, when you try to drag one object, the drag is going to slowly stretch the surface, but the grip is going to be there. But the moment it starts slipping, once it starts slipping, can it grip the same way as it was able to grip initially when it is at rest? It won't be able to do it. Which means what? On the go, friction drops. It won't be the same. The friction value kind of is different when it is at rest or when it is moving. So we have two kinds of coefficients. One is mu s and the other is mu k. S stands for static. So coefficient of static friction, and this is kinetic friction. We have static friction and kinetic friction. Static friction obviously means the objects are not moving yet. Then you apply that. Kinetic friction is when it is moving, so you apply that one. So normally, mu s is greater than mu k. Let's say for rubber, your rubber tires with the road, the coefficient of friction is probably 0.8, 0.9. Okay? That is if it is at rest. The moment you slam brakes and it starts gliding, then it's kinetic, and that drops. That's why once your car kind of starts skidding and all that, it's hard to get it back to control because you're talking about kinetic friction now, not static friction. So that's why it's always important that you don't skid or hydroplane. Now what's happening in hydroplaning is that your tire has to have a grip on the road. You don't want a fluid to come in between and create fluid friction. So hydroplaning is when your car is gripping on the road, all of a sudden when there's a puddle of water and all that, it gets a layer of water in between and the wheels will go crazy, spinning faster, and the direction of the car cannot be controlled by you then in that period of time. So the car kind of drifts and goes, so without your control. And because of that, you panic and you turn the wheel because you don't want to go that way. So you panic and turn the wheel. And when you turn the wheel, suddenly the grip comes back and then the car twists. You know? So it's a pretty risky thing in the hydroplaning. So if at all it hydroplanes, don't twist the wheels and make it a bigger mess. Let it get the grip back again and then move on. Okay, so yeah, so how do you understand this better? Like, let's say, for example, imagine there are lots of railings on a fence, and you're standing next to this fence, and suddenly a student is coming and pulling you. And as soon as the student starts pulling, you're holding on to one of these poles, and the student is pulling you. And he pulls with more and more force, so you're able to give a nice opposition right there. But the moment your hand slips off one of those, you're already on the go. But on the go, are you still able to oppose? You will be able to grab, right? But can you grab it the same way as you have grabbed earlier? So that's why I said coefficient of static friction is a bigger one compared to coefficient of. And so the limiting value of friction you can have Fs is equal to mu s times normal reaction if it is not moving, or Fk is equal to mu k times normal reaction. The normal reaction is an important element here. Okay? Questions here so far? Good?
So we give our answer in a relation to this coefficient, like we wouldn't have to define it like that's number.
You mean to find that out?
Yes, like we don't, like will we ever be given like.
Oh,
actual
you'll be
numerical
given the
value?
mu s and mu k and all those things, yeah. You don't have to memorize any mu k or mu s for any surfaces because there are millions of surfaces pairs. Now, the mu s and mu k is for a pair of surfaces, right? It's not for, what is for steel? No. Steel with what? Steel with rubber or steel with concrete? They're all different. So the coefficients won't. Now, if the question is asking you to find the coefficient, then that's a different story. But generally, those numbers will be given to you, and they'll all have no units. It'll be decimal normally, and we'll see through some problems. Now, let's see how these things apply. Let's see how they apply. Let's take a problem that you've done earlier. Let's say it's a 100 kilogram object sitting on a surface. It's a 100 kilogram object sitting on a surface. The coefficient of static friction is 0.6. The coefficient of kinetic friction is 0.4. I've given it to you. So between this block and this surface, there is a coefficient of static and kinetic friction. Now, what is the amount of friction right now?
0.
0. Now, if I start pulling it gradually from here, which way will the friction be acting?
Opposite direction.
Opposite way, and that's going to be here at the bottom. So that's going to be the friction. So if I pull with 10 newtons, this is going to be 10 newtons backward. If I pull with 20, it's going to grow up to 20 again. Question is, find the minimum force to just set the block in motion. What is the minimum force to just set the block in motion? How much should be the minimum force? It should be the limiting value of friction, right? So before you do anything, first what do? You've drawn the diagram. Next, draw the forces. Okay, the force downward is 980 newtons. What is upward?
980 newtons.
980 newtons. Newton's first law applied already there. Now, normal reaction is 980. Is there a friction acting here? Static friction is coming in. Yes, how much is static friction?
0.6.
Can you find out how much it is?
588.
So 0.6 times 980, which is 588 newtons. So the limiting value of static friction is 588 newtons. You need to exceed that. So basically, if I apply 588, then I should be able to get it going. Right? So the minimum force required is the maximum friction can oppose me. How much is the maximum friction? 588. So it starts slipping. If we continue to apply 588 newtons to the block, what consequence can be seen? If we have continued to apply 588 newtons to the block, what consequence will be? Will it result?
Accelerate.
It will accelerate. Why? Because the kinetic friction is now lesser because already the block is moving. Now 588 is not going to continue to oppose you. What is the new friction force? The new friction force is 0.4 times 980, which is 392 newtons. That is the kinetic friction. You are still pulling forward with 588. What is the backward force? 392. Balanced or unbalanced? So it is definitely going to accelerate. So apply second law. Net force equal to ma. So 588 minus 392 is equal to 100a. So find out a. 1.96 meters per second square. So the thing is going to accelerate. That's a consequence. The block is going to accelerate at 1.96 meters per second square. Any questions? All right, let's continue to. We did a problem before with the block. The mass was 10 kilograms, and you're pulling it like this at 40 newtons at an angle of 30 degrees. You see that problem? Okay. Now let's say the coefficient of friction, static friction, is 0.3, and the coefficient of kinetic friction is 0.2. What will be the consequence? So let's work it out. Again, as before, what do you do first? Draw all the forces. So this one has got a force downward, how much? And there is a force here which is how much? NR. And then this one, 40, has two components. There's a 34.64 newtons sideways. And how much is this? 20 newton upward. So when you split this 40 into two components, we get the forward component is 34.64, and that is 20 newtons. So since this block is not moving up or down, the net force vertically on the block should be 0. That means the total upward force must balance the total downward force. So the total upward force is NR plus 20, should balance the downward force of 98. And therefore NR is, so the NR is 78 newtons. Now as this block is moving that way, let's find out static friction. Apply static friction and see how much is static friction. How much is static friction? 0.3 times 78. How much is 0.3 times 78? Is it bigger than 34.64 or smaller? If it's bigger, you know what will happen? The thing is not going to go anywhere. You can pull it with 40 newtons, but it's not going to move. What is the answer actually? 0.3 times 78 is how much? 23 or something, which means definitely it's going to move. So it is definitely going to move, right? So now you're not going to use this. Since it's moving, go for this now. How much is the friction? How much is the friction here? Friction, kinetic friction is 0.2 times 78. 15.6. Now look at the two forces which are acting horizontally on the object. One is 34.64 forward, the other is 15.6 backward. So the net force is equal to MA. So 34.64 minus 15.6 is equal to NA. So acceleration is 1.9 meters per second square. You can see how we are incorporating friction into the problems, right? Any questions about it? Any questions how the friction gets into the problem and how you are actually not forgetting about it? All good? Yes.
So once you find out that the static friction is less than
That
the
means
force,
then you conclude it's already moving. So we don't want to apply this anymore because then this is.
That was my question.
Anything else? Did you check the videos previous class?
Yeah.
Now I'm going to change this problem a little bit. Instead of pulling that box, I'm going to push it now. You're going to push the box with the same force, 40 newtons, and the angle is 30 degrees. Will it make a difference? Instead of pulling the box, if you just push the box at the same angle, is it the same or different? Like imagine this box. I'm pulling it like this, or I'm pushing it like that. Let's find out. What do you do? As usual, draw the forces. There's one force already here. And there's a normal force here. Split this into two components. What are the two components? One of this, the horizontal component is this one, which is 34.64. And where's the vertical component? Which way? Downward facing. And the 20 Newton is acting downward. So how much is normal reaction?
118.
The normal reaction is 118 newtons. Because, do the same thing. The total force upward should balance with the total force downward. Downward, there are two forces, 98 and 20, both are downward. And there's only one force upward, which is normal force. So the normal force has to be 118. So when the normal force has gone up, then next thing you should see is how much is the static friction. Can you calculate how much it is? How much is the static friction? You'll see something interesting.
35.4 million.
How much?
35.4 million.
35.4. How much is this forward force?
34.6.
So the maximum frictional force is 35 point something, and this is 34.64. So you're on the verge. It won't move. It's not going to move. See, previously you pulled it with 40 newtons. It was moving with an acceleration of 1.9. Now it's not moving. I'm pushing with 40 newtons. It's not moving, but it's about to go. Now your friend comes in and just gives it a little push, and then it starts moving. So imagine someone came and just touched it, and it started moving now. When it starts moving, what's the friction force? So initially it's not moving, and when it starts moving, how much is the friction force that is going to fight? You're going to fight with? It's 0.2 times. How much is that? 20. So you're going to fight only 23.6, but that release was required. Unless someone came and touched it like that, it won't go. You'll be pushing with 40 and it's not moving. But someone came and just gave it a little push, and then the whole thing becomes kinetic. And once it becomes kinetic, this is the force. Forward force, 34.64. Backward force, 23.6. Net force is not zero. So net force is equal to MA. So what is it? 34.64 minus 23.6 is equal to 10A. So what is the acceleration? How much? How much? 1.1 meters per second squared. You can see clearly which was easier, pushing or pulling? Pulling. Pulling is easier than pushing. So if there's a box that needs to be moved, tie some rope or something and pull it like this, it'll be easier for you to make that move happen compared to push it. So when you push it, what's going to happen? You are applying a downward force which adds to the normal reaction, which increases the friction. So you end up fighting more friction. So when you pull, the component of the pull is going to be acting upward, releases the normal reaction, relaxes it, which means the friction also will come down. So if the question is generally asked, why is it easier to pull a lawnmower than push a lawnmower? The answer is this way. See, push and pull is basically the same direction, but when you push it, you're adding to the normal reaction, which increases the friction. When you pull it, you're literally lifting it off. Yes?
And if you're pulling like somehow in a downward force, would that also be a hard point?
That's the same thing, yeah. And if the box is such a big box, then you're kind of pulling it from here. Yeah, I mean, like normally when you're this tall, if you have to be pulling it downward, no, the box must be really big. So yeah, when you pull it downward, it's the same consequence. The direction of the force matters there. Any questions on this? Good? So now we have an inclined plane, which is not friction-free, and it's a connected object system. How do you tackle this? So which way do you think it's going to go? 15 is going to, oh, I didn't tell you the angle. How can you be so sure? I didn't even tell the angle. Well, if I put the angle at 60 degrees, it's going to go down this way. But now it's 30 degrees, so 15 is going to be pulled out, and the 10 is going to go down. Okay. Again, that's a possibility, but whether it's really possible or not, we have to investigate. So how do you investigate? Draw the, and then draw the forces. What is this force? What is upward? No normal reaction. Tension here. It's a cable, so there's no normal reaction. Tension. Tension is upward. So those are the two things for that object. What about this object? What's pulling it up? Is it the same tension or different tension? Same tension because it's one string. What else is acting on this? Now remember again one more thing. We are not going to go do it gravity downward and all those things again. I've done it already once. Did I discuss the inclined plane once? And I said, if at all you get inclined planes in future, use that directly. What is the force that acts downward? mg sine theta. And what is the normal reaction? mg. Can you flip the pages backward and see where it is written that way? Go back and see where it's written. I've done it. Go to the inclined plane. You see it? So I have already resolved it. You know, we drew the normal, we drew the weight and we took the angle into consideration. We split that weight into two components. We've already done that. You don't have to do it again and again for every problem. You just use those directly. What is the component of gravity down the plane? mg sine theta. What is the normal reaction when something sits on an incline? mg cosine theta. Get the values. How much is this? 15 times 9.8 times sine 30. How much? 73.5. What's the normal force? 15 times 9.8 times cosine 30.
127.3.
127.3 is a normal force. That's a normal force. The normal reaction. Now, you can see that this is only 73.5 and that is 98. Can you see that? From that side it's pulling 98 and from this side it's pulling how much? So, which way do you think it can go? So let's assume it's going to accelerate that way. If it is going to move that way, which way is friction now?
Kinetic.
If the tendency is to go that way, then friction is backward. How much is friction? Now we can try this. Is it going to begin movement or not? Check it out and see. 0.2. 0.2 times, put all those things and see.
25,
How much?
25.5.
25.5.
Yeah.
So what's happening there? It's just not moving. If friction is going to be, if it is static, if I just release it from there just like that, what is expected to happen? This is how much? Friction is how much? 20?
25.47.
Yeah, that means when you add them up, it is 98, right? So it's kind of balanced, which is not, it's on the verge of slipping, but it's not going to move. You see it? But then if I just kind of just knock on the inclined plane a bit like that, it is now free. Then apply this one. Do you understand what I'm saying? See, sometimes you may be seeing an object sitting on an incline and not moving yet. Look. It's not moving yet. But if I just disturb this a bit, it will start moving. Let me take it up there. Yeah, it is on the verge of moving, but it's not moving yet. But if I just, the moment I touched here, that little vibration became, that little vibration released the static friction and made it. So what is the kinetic friction now here?
12.73.
12.73. That's the coefficient, that's the friction force. How? It is mu k times normal force. So it's 12.73. Now, what do? Go to this object and apply Newton's second law. 98 downward minus tension is equal to ma. Then go to this object and apply the same thing. It's going that way, so which is bigger? This is bigger or these are bigger?
Tension.
So tension is bigger. Tension minus 73.5 minus 12.73 newtons is equal to 15A. Simplify this, you get T minus 86.23 is equal to 15A. So 86.23 minus, tension minus 86.23 is equal to 15A. Adding them up will eliminate T. So add them up, you can eliminate T, and whatever you get is 11.77 is equal to 25A. So A is equal to 0.47 meters per second square. So the whole thing is going to now start accelerating like this at 0.47 meters per second square. Question? Yes.
What was the part?
So that's the example of connected objects where one object is suffering some friction. And how do you incorporate friction into your problems is this way. All you need to know is how much is the normal force and where's the coefficient. Use them, go. Let me give you some different variety. Imagine there's a box on the ground. There's a box on the ground, like this Dare to Care box. Okay, so there's a box on the ground, and if I give it a kick, not because I don't dare to care, I do care, but I'm just doing this for an example. So if I'm going to kick, let me put some weight inside. If I'm going to give it a kick or a push, stopped over there. Okay? So I'm going to base my questions on that. So that's a box of some mass, I don't know how much. I gave it a kick and made it go at a speed of 2 meters per second. And the box went on and finally came to a halt after moving. How much distance was that? 2 meters? Right. The box stopped after 2 meters. So this is the initial velocity. And what's the final velocity? Okay. Now, why did it stop?
Friction.
There's a frictional force acting on it. Which way?
The
Backward? Do you know how much it is? Can you tell me an expression at least? It was moving, right? And therefore, it's a coefficient of kinetic friction. I don't know that. Question is, what is the kinetic friction coefficient between this box and the floor? That's what we're trying to find out. So we don't know this. What's the normal force? What's the weight? And what is the normal force? mg. Okay. See, I'm not working with numbers. I'm just working with variables now. So this is the frictional force that's coming in. And because of this frictional force, it is suffering a deceleration. Is it possible to find the deceleration by any chance? Can you? How? Equations of motion. Go ahead. You have initial velocity, you have final velocity, you have displacement. What more? Find A. You have initial velocity. You have final velocity. You have displacement. Can you find A? What's the equation that's going to connect all those? Vf square is equal to Vi square plus 2Ax. Substitute. 0 equals to 2 square, 4, plus 2 times A times 2. So 0 equals to 4 plus 4A. So what is A? Negative 1 meters per second squared is the acceleration. Alright, so you got the acceleration. If that is the acceleration, how much is the force? Mass times acceleration is a force, right? So this force that you're seeing here is mass of this object times that acceleration. So mu k times mg is the same as mass times 1. I'm not putting minus 1 because this is a backward force also, right? This is a backward force. So I'm just getting the numerical value of the acceleration and I'm just plugging it here. So m cancels off. Can you tell me what is mu k then? One divided by, this is 1 and this is 9.8. So what is mu k? 0.1. 0.1. No units. So we just discovered the coefficient of friction between the box and the floor. A simple experiment. How do you apply this? Imagine you are driving a car at a certain speed and then you hit your brakes, slammed your brakes because you were anticipating some accident or something like that. So you slammed your brakes and